I just will read it. Over the last few decades, computerization changed dramatically the outlook of modern scientific and educational culture. At the same time, it created the need of rethinking the aims of school education, especially in mathematics. In pre-computer era, mathematical education of the middle level was mainly aimed at mastering the skills of numerical calculations and symbolic algebraic transformations required in applied science as well as in industry. The main efforts of teachers and methodologists were directed to this objective. Now, the widespread use of computer technologies has made this goal obsolete. At the same time, the increased dynamics of professional life poses new demands on mathematical education. Besides the mastering of the traditional curriculum, one expects from modern students the achievement of more ambitious goals that go beyond mathematics itself. In particular, great emphasis is laid nowadays upon the development of scientific thinking achieved by means of mathematics. The role of geometry. A special role in development the skills of creative thinking belongs to geometry. This fact has long been recognized by the theorists of mathematical education. Hans Freudenthal, among others, insisted on the point. An advantage of geometry, so Freudenthal, consists in that it can be taught and mastered, at least at the early stages, based on rather simple operations with real tangible objects. So, this suggestion is a concretization of a classical thesis of Vygotsky on real practice underlying both thinking and speech. The main idea of our paper consists in that the special role of geometry is due to the diagrammatic character of its content rather than the axiomatic form of its exposition. The value of practical operations in geometry consists in that thinking with real object compels its students to find intermediates between what is given and what is required by drawing auxiliary constructions, not by logical reasoning, finding the middle term according to Aristotle, but by drawing auxiliary constructions. This type of diagrammatic thinking can be applied outside geometry proper, namely in arithmetic and algebra. The examples will follow. The first example is very simple. Usually the subject, the formula for the area of triangle is studied like that. One memorizes the formula itself and then one tries to apply it to different situations, to different numerical values of sides and heights of triangles. Let's say it frankly. It's a normal situation. What we propose to do is to replace it or make like an alternative, the following reasoning. Let's put the question for the students to find the area of triangle. The first step would be to reduce the triangle to a figure of which it is known how to find the area. And the simplest figure is, of course, a rectangle. And the most natural way to combine a triangle and a rectangle is to ascribe a rectangle around the triangle. Now the second step is also very simple. We draw the height from the vertex up on the base, and now we can clearly see why the formula actually holds, because there are 4 triangles on the right side, and we see that each two of them are equal. It's obvious. Actually, this simple example may be expanded to other situations as well. There are more. If this angle is obtuse, we can find the area of this triangle by dropping the height. And then this is a whole triangle. It's of course obvious, but we can make it without subtraction. We can, for example, use a more simple tools like that. We can divide the base, taking a half of it, then drawing the auxiliary line. This is a construction I was speaking about. And when we can do a simple transformation by putting this part of the triangle here. Now we have a parallelogram which is equal in area to the given triangle, and we have to find the area of this parallelogram. And this is done, for example, in many, many, many ways. The most simple of which being drawing a diagonal, and by transferring this triangle to the right side. Then of this, we can make, let me draw here. We can take this triangle and put it here. And we finally have a rectangle which is equal in area to the given triangle. Our next example is a little bit more complicated. It's the application of this geometrical or diagrammatic reasoning to algebra, to the simple algebra. We have algebraic identity on the top, and we have to demonstrate it. Well, the usual way of demonstrating algebraic identities is to, I don't know how to say it in English, раскрыть скобки. So making simple transformations with symbols. But when we perform such or let's say students perform such transformation, they learn nothing except for mastering these symbolic skills. We think that a good alternative to that would be this diagram, which shows at once the truth of this identity. Should I explain what? Okay. And I called it the propeller. Actually, one of my students called it the propeller, and I like the term. You can see that there are 4 blades and an axle in the middle. And this propeller can be used for solving all kinds of squared equations. Just one remark. The idea comes from old Babylonian mathematics, in which 1,500 years before Christ, such a diagram was used for solving squared equation. This is an example how to solve the equation of the form x squared plus px is equal to a capital. At the basis of our reasoning is this rectangle. This rectangle is exactly what is here. So x multiplied by x plus p. And if we combine these four rectangles in a way which is given on the diagram, we see that that the diagram actually corresponds to this half symbolic formula in which p is equal to 2 and a is equal to 15. And now, as we know the value of p and the value of a, we can calculate the area of the square of the side to x plus 2. And finally, we can find the value of x. Of course, we can find negative solutions of this equation. Another example, that's the diagrammatic solution of the equation of another form. It's like that. I wouldn't much more explain that. It's made in exactly the same way. So we take a rectangle, one side of which is x and another side x minus p, and we take four such rectangles, arrange it in the form of propeller like that, and we find the solution. There remains now the last type of squared equation, which I wouldn't comment on. We can obtain two solutions from this last kind. In the same way, we can find solutions of the system of equation of the form like that. It's the same diagram, and many other systems of equations not higher than 2, of course. My two last examples are from arithmetics. It's not anything which is taught on the middle school level, but probably for more philosophically, so to speak, oriented students, it will be of interest. The problem is how is related a number and its square. It's very easy to see that if a number is odd, the square of its number is also odd. And if a number is even, the square is also even. But other way around presupposes the demonstration by contradiction, which is something which is not very natural for the students, especially for the students in the humanities, which we, with my colleague Sergey Bychkov, taught for a while. Now to we do not use this argument demonstration by contradiction, but we can use a simple diagram. I think that's it's easy to see on sorry. No, I did something wrong. Куда нажать? Извини. Ну вот, испортил аппаратуру. Ага, все, спасибо, я дальше уже сам. Да, let's see. We can arrange a square number like a real square with the side n, and we can выделить, so draw the diagonal of this number. And we can see that the number n square is equal to the diagonal, that's the number n, it's exactly the number n, and two so-called triangular numbers a. And from this diagram, we can see that if the number n is odd, n square is odd, and if the number n is even, the number n square is odd, because this term, this intermediate, which we have drawn, is odd, is even. And also the other way around, if n square is even, n will be even because 2a is even. And if n is odd, n square is odd, n is also odd because 2a is even. Еще время. And the last theorem, it's a little bit more advanced. It's from Euclid's Elements. If you consider a number m capital, which is equal to the product of two numbers n and p, and we know that the number n is odd, then the number m is odd if and only if the number p is odd. So that the situation is rather similar to the previous case. To demonstrate this statement in symbolic way is very easy in one way, so that if the number p is odd, that the number m capital is odd, it's obvious. But the other way around, again, presupposes the demonstration by contradiction. By using this diagram, we can we do not use this kind of demonstration, because if the number n is odd, then we can, when we can discern this extra pebble, so to speak, which is responsible for oddness of this number, these two parts on the top and the bottom being equal, and then the number m will be split into three parts. Two parts are equal, and the line which matches exactly the number p. And now from this picture we have this quasi-algebraical formula which gives the answer to our question. If the number p is odd, the number m will be obviously odd. And if the number p is even, number m capital will be also even. And the other way around, if the number m is odd, the number p is odd. Number m being even, number p is also even. Okay, I just finished. A couple of days ago, I was kind of struck by a paper published in The Guardian. It was published on March 2019, also 6 days ago. And the paper is, the heading of it's Max Anxiety Causing Fear and Despair in Children as Young as 6. And it starts with the remark, children as young as 6 feel fear, rage, and despair. Such a strong words. as a result of mathematics anxiety, a condition which can cause physical symptoms, not only psychological, physical symptoms and behavioral problems in class, according to a study. And that goes on, goes on, goes on. Actually, when we started to teach students in the humanities, it was a course in mathematics, we had the same problem. The student at the age 6 and at the age 17 and 18 have the same problem. They fear mathematics, they hate it, and what we designed was an alternative to the traditional symbolic mathematical teaching. Thank you.
Thank you for the interesting report. So many interesting reports from Russian Federation. It is a pity that it was not possible earlier to participate for Russian people in PME meetings. And now we pass to the questions and discussion. My first question is, could you give a more precise and concrete formulation of the diagrammatic thinking?
Say it again. По-русски.
Точное определение диаграммного мышления.
Еще раз.
Что такое диаграммное мышление? Diagrammatic thinking.
Well,
earlier I met this term in some other papers by mathematics educators. For example, Eric Christian Wittmann and so on. Willy Dörfler.
Okay, just to put it in logical, philosophical terms. So our usual formal thinking in mathematics is based on Aristotelian logic. So there are two statements which we try to relate by a middle term. And this is also a kind of logical statement which is in between, which have a characteristic of the first statement and the last statement. And in mathematics, the usual way of doing that is also involves the demonstration by contradiction. So they suppose an alternative situation and trying to make a contradiction out of that. That's what students in the humanity fear, actually. The diagrammatic thinking is something different. We, so to speak, think without by manipulating with objects. We find a kind of intermediate objects which provide us access to the solution of the problem. So we can see the solution, actually. Of course, logic is involved, but not on that high level as in usual formal mathematics.
Thank you. Some more questions?
Next question. Thank you very much for the lovely presentation, diagrammatical thinking. You just said that we just need to manipulate objects to see the diagrammatical thinking. What do you think about the dynamic geometry, the role of dynamic geometry in materializing this diagrammatical thinking? Now we use technology more and more. That means there are some softwares like GeoGebra that brings together geometry and algebra. Do you have any comment on these, using these softwares to promote this diagrammatical thinking?
Так, кто-нибудь переведет?
Ну, это вот как можно использовать программы динамической геометрии, ну, типа GeoGebra, вот для развития диаграмматического мышления.
I am not qualified to answer this question, sorry. I never did it. Maybe, I don't know. Actually, I think that the possibilities of computer programming are very good now, so that why not? That all these diagrams can be drawn not manually, but by computers. And
Can I comment the question and not answer? I think that in dynamic geometry we have media operating with geometrical object, but now we can see how we manipulate with algebraic objects using geometric form on this. So I think that diagrammic thinking is applicable to algebra, not to geometry, because it's geometrical view on algebra. And now I think it is very important to discuss what to do with algebraic calculations, because now we have many good computer programs, for example, Mathematica, which can do all algebraic manipulations. And what will be in the rest? What all the students must know in school about algebra. And I think that it is these examples show the same as Wertheimer think about how to teach mathematics. They must understand using their ordinary ideas which come from the childhood. Because in algebra we have good instruments by manipulating with very complicated formulas, and what of these formulas must be eliminated from school, and what technique must be stayed in school. It's a big question.
Some more questions, comments?
I would like to ask about how do you understand the term objects that you are using. To contribute to the question, I would think that these dots signify other objects. They are not objects in themselves. So would you make it a bit more?
okay, it's a very good question. Well, it's I'm a historian of mathematics. Behind these circles, simple circles, are pebbles of old Pythagoreans. Yeah. They were real objects, and the old Pythagoreans, of course, didn't draw that, something like that. They just manipulate these pebbles on the sand. And this is a stylization, of course. They are not real objects, of course, objects. But it's still, they have a geometrical form, unlike the numbers, which are only symbolic.
Thank you. I really enjoyed this. You didn't mention explicitly proof and proving here, but there's some discussion in the research on proof in mathematics that they differentiate between proofs that prove and proofs that explain. And I see what you're doing here is something that these, especially when you mentioned the humanities students who don't like the proving through contradiction, because I think that's a problem that it doesn't explain. Maybe you want to comment something how this relates?
That of course, that to prove does mean that to prove with logical means, and to explain, we can explain on pictures. May I say something personal? 2 or 3 years, I tried hard to implement some ideas from the history of mathematics to the students in the humanities. And the point at which I failed was the demonstration of irrationality of square root of 2. You know that the usual demonstration is so unnatural, it's made by contradiction. And so that from that I started we started to invent these pictures to explain something and not just to demonstrate. It's
Yeah, thank you for this nice demonstration. I'm very fond of diagrammatic reasoning all the time. I think that's real mathematics, and doing that is something that always gives me some kind of enthusiasm as a mathematics teacher and mathematician. What I think here, and Marco has pointed to that, is that this is a kind of visual proof. So that's what here is. And I think the problem that might appear in this kind, these are figured numbers, and the figured numbers are, of course, finite. Yeah, so it's a finite number of figures and of points, and the students have to see into them the structure, and that's, I think, the difficult point. So we are working with these also with students, with pupils from at grade 5, 6, or primary level, and the point where they fail is that some of them cannot see the structure into that. And I think that is a difficulty that might appear also in the humanity. Can you say something about that? Did you see this, observe this, or comment on this?
Я правильно ли понял вопрос? Well, first of all, I never worked with children of the age 5 and 6. My own to that point when I developed this mathematics, when we developed this mathematics, already grew up. So that there were only students in the humanities. So people who had behind them a bad experience with formal symbolic mathematics. And what we tried to do, just to show that behind this symbolic, garbage for them, is a real mathematics with real forms which everybody can do. I had a student which liked very much transformations like that. They are very fascinating because if this parallelogram is very obtuse, you have to have very many divisions and very many transformations, but you have to have an idea that you should reduce it to rectangle. I don't think that it's very realistic to replace symbolic and formalistic mathematics totally from the curricula, but to supplement it to a certain degree with such diagrammatic figures. One shortage of this diagrammatic mathematics, for example, for the solution of algebraic equations, we cannot obtain negative solutions. There are problems with the demonstration of arithmetical theorems, especially about prime numbers and things like that. I fear they can be demonstrated only by contradiction. So it's not a panacea. It's just an additional element of mathematical. And what I'm thinking about, I never tried. I think that students with disabilities, for the student with disabilities, such a mathematics will be more accessible for than symbolic mathematics. I had one case of a student with a very severe psychic disability, and she did very well these exercises in the object-oriented mathematics, actually. And she never tried symbolic solutions. She could not just grasp the idea.
Evgen, about the table of multiplication, commutativity.
That's a good suggestion. Do you know, yeah, you surely know, why 3 times 5 is equal to 5 times 3? Do you think it's a just a jokes? No, the children in elementary school usually give the answer that this number is larger than this. For the first grade and even in second grade. So they think that, and the solution is very simple. We have a rectangle corresponding to the first product. And if we rotate this rectangle, whatever, clockwise, or we obtain exactly the second part. It's just a very simple illustration of the idea of what mathematics with objects is about.
Professor Kaplanovich, very short question.
Спасибо. Если Professor
хорошо,
Kaplanovich,
по-русски.
and would like to go on the scene and show you my question. It will be easier. I've got 3 questions about understanding. The first question is, we have many studies starting from Hegel and etc., and then going through Rubinstein, Vygotsky, Piaget, John Brunner, and others, Poincaré. And those studies, they say that phylogenesis isn't repeating the oncogenesis. There is no historical development. I'm not against the history of mathematics as a separate course, but they all said that there is no necessity to repeat those old things during the education. As to the second questions, I liked very much your examples, but there is a classifications by Poincaré and explained by Krutitsky of about mathematical thought. Poincaré showed that there are 2 kinds of thinking, geometrical and algebraical one. It's Poincaré, not Krutitsky. And there was a famous joke when the teacher was explaining what was it like, put in the parentheses, and Bobochka couldn't understand it. But then he understood that if you take a triangle with a side a plus b, you have this formula. It's an old joke, you know it, yeah, of Rousseau times. And so we have this kind for one kind of persons, and we have this kind of proofing for a second kind of persons. And in the third place, as I understand the mechanism of those problems, interesting problems you've told us about, I'll try to picture it. So it reminds the famous problem of Rubinstein when he asked to find this A, this B, and you have to find the surface area of this rectangle and parallelogram. And the idea was that you had to analyze 2 right triangles, and it was easy to calculate. And he explained it with the mechanism reformulating those ideas. And we have plenty of those items. So can we see it as a manifestation of this Rubinstein law?
Okay.
2 main thought mechanisms.
Thank you for this question. I have to say just 2 words. It doesn't mean that the teaching has to recapitulate the historical development. It's wrong. Historical development is very windy, but we have extract the logical part of it and use it in teaching. And for the other questions, I don't say that we have to replace usual algebraic thinking with diagrammatic thinking. It's just a means to help students to understand, probably to understand better the algebraic thinking.